Okay, well, thank you so much for the introduction, and thank you for inviting me. You'll see the title is actually not what it says. And the reason is because once I saw where I was placed in the list of speakers, i.e. first, I thought it would be a good idea to just give more of a broad overview of some of the really amazing properties of optical vortices. I think that'll set up the conference better than me just banging on about chirality for an hour. So the title is now called Structured Light at the Nanoscale. What I really mean is tightly focused optical vortices. So I'm going to talk about what happens when you tightly focus optical vortices and all the extraordinary properties that you get when you do that. Okay, so I'm going to use a unified framework. So I'm going to use a mathematical framework. Okay, I hope we're going to try and follow along step by step because it's the exact same maths which will describe all of the properties. So I'm not going to throw different mathematical techniques at you, numerical, analytical. I'm going to use the same one, okay, which hopefully will give you sort of your own sort of ability to think about these things at the fundamental level. Okay? We'll have a quick revision of structured light, light as a transverse wave, and optical properties of paraxial beams. These should all be well known to you. And then we'll look at the fact that light is actually not a transverse wave, okay? And that's what gives it all these amazing properties that we'll talk about for these non-paraxial beams. I'm going to look specifically at the intensity, spin, and the chirality. Okay? And then we'll look at some key points to remember. So what is structured light? Structured light is essentially any beam of light which has an inhomogeneous intensity, polarization distribution, or a phase. Okay? And it comes in all different flavors. There's a lovely diagram from Andrew Forbes' paper in Nature Photonics. You have two-dimensional, so you've got these, and do it this way, you've got these varying polarization ellipses, so that's obviously a vector beam. Okay? You've got a varying phase and a varying amplitude in 2 dimensions. You propagate the beam, it changes, 3-dimensionally structured light. Take a point in space, okay, and allow time to flow, and the structure changes, 4-dimensional structured light. These are actually very complicated structured light beams. What we're interested in, optical vortices here today, are actually really simple structured light beams, okay? They're scalar phase structured light beams. This slide's going to be a bit redundant because we all know what optical vortices are, but just to remind us, okay, we have a plane wave, okay, propagating along Z. Our polarization is in the transverse plane, X and Y. The OAM operator in the Z direction is clearly this plane wave is clearly not an eigenfunction of this operator. There's no azimuthal dependence, so plane waves don't have OAM. Simple. Send it through something like this, a spiral phase plate, and you'll give it this helical phase, which you describe by EIL phi. L we call the topological index, ranges from -infinity to +infinity in integer values. Okay. Now, if we look at what happens with the operator onto this electric field, we find it's an eigenfunction with an eigenvalue of LH bar in the Z direction per photon of OAM. Okay, so that's a real simple way to show that vortices carry OAM. Okay, and of course this L ranges to ±infinity, so you can add more and more twist. Okay, and of course you get the distinctive characteristic ring-like intensity for these beams. If L equals 0 or M equals 0, I stole this off Wikipedia, then of course it's just a Gaussian beam with no OAM. Lots and lots of applications in the paraxial regime. So we have optical manipulation, data transfer, and quantum information. So I believe this is true. The largest quantum number ever entangled was 10,010 H bar by Anton Zeilinger using an OAM photon. Okay, so lots of established applications, okay, and established structure to these beams. A little bit of undergraduate physics. So light we treat as a transverse wave normally. So if it's propagating along Z, it'll be polarized in X and Y. Alpha and beta are Jones vector coefficients. So if alpha's 1, beta's 0, it's an X polarized beam going along Z. Beta's 1, alpha's 0, it's a Y polarized, so on and so forth. And of course, that polarization ellipse is quite general in the 2D plane. We can go from linear to elliptical to circular. So if you have a pi over 2 at a phase relationship between the X and Y, you'll get elliptical polarized light. And obviously in the extreme, you'll get circularly polarized light. And that can go right or left. And we can describe all of the polarization properties of a transverse wave or a paraxial beam using the geometrical representation of a Poincare sphere. So map all the states of polarization on the surface for fully polarized light. As you go in, partially polarized, and in the middle, unpolarized. So for a transverse wave, a paraxial beam, you can describe all of the polarization properties using this very simple undergraduate description. Okay. Now, why are we interested in light? Because it carries optical properties, and they carry lots of important ones. Okay. The electric field contributes, the magnetic field contributes to all these amazing optical properties. Today, I'm only interested in the energy density, essentially the intensity, the optical helicity or chirality. Now, I'm only interested in monochromatic beams, so I'm going to use chirality and helicity interchangeably. They are not the same thing in general, but we can be safe today to just call them the same thing. And the spin angular momentum density. Okay? So that's what I'm going to be interested in today, these optical properties, okay, of these beams. Now, just a revision, for paraxial beams of light, we get very well-known results. So the energy density is just the intensity divided by c. The helicity is disproportional to the intensity times this thing sigma, which is basically ellipticity, okay, which ranges from 1 to -1. So 1 and -1 are the circularly polarized states. 0 would be linear polarized light, and in between would be elliptical. So linearly polarized light, as a paraxial beam, does not have helicity, for example. The canonical momentum density, okay, which has the well-known longitudinal part in Z, but if you've got a vortex beam, you'll also have the azimuthal component, and that leads to the orbiting of particles around a beam. Okay, it's not the OEM that does that, which is often said it does. And then we have the spin, okay, which is just the helicity times the direction of propagation, and the OEM density with the famous Z component proportional to the topological charge. Okay. We can do the quantum theory, and we get the canonical per photon values. Okay, so this is all pretty well established stuff. Applies to paraxial beams, well known. Okay, but light is not a transverse wave. Okay, plane waves, yes, they're transverse, but they're fictitious. They don't actually exist. Okay, these beams do not. You can't have beams which extend into infinity like a plane wave. Okay, for any real electromagnetic beam, you've got a transverse cutoff, right? In its distribution, it's not actually a plane wave, or it can't actually infinitely extend. Okay, and what you actually find is that the transverse divergence of these beams, okay, for any real electromagnetic beam, you cannot simultaneously satisfy both of these relations here. Okay, what does that mean in English? It basically means that for real electromagnetic beams, you'll have to have a longitudinal component to your field. Okay, there'll have to be a Z hat component to any real electromagnetic field. It's not transverse. You'll have to have X hat, Y hat, and a Z hat part to the polarization. There's a deeply fundamental reason for this, which I quite like, is that if we have recourse to Heisenberg's uncertainty principle, this seems to explain everything. Okay, the uncertainty momentum position has to be bigger than h bar over 2. I have a photon. Its momentum will be h bar k in any given direction, so kx, ky, and kz. Okay. Now, what happens is that if you've got a transverse wave, okay, you think that the beam is going all along Z. Okay, it's all along Z, polarization up here. So you think its wave vector is all along Z. This tells you that can't be true because the kx and ky parts have to exist because of this uncertainty in position. So you think about a photon, okay, and you put it into a smaller and smaller and smaller and smaller and smaller space, what you're doing to the uncertainty, okay, you're decreasing the uncertainty in where it is, its location. That makes this uncertainty in position a small number, which makes the uncertainty in momentum large because you're dividing by it. And so the smaller and smaller you, oops, didn't mean to do that. The smaller and smaller you focus your beams, the larger and larger these kx's and ky's will come up from your kz propagating beam. Okay? And to ensure the transversality condition, what that means is if I've got kx's and ky's, I need ez to make e dot k 0. So if you think a nicer way to think about all this maths is to look at this a typical diagram for focusing. Okay, this is your paraxial beam. All right, it's x-polarized, it's propagating along z. K is aligned with z. Each individual wave vector of the plane wave spectrum. Okay, that's fine. That's a paraxial beam. It's transverse. As soon as you focus it, okay, to keep this e dot k, all the constituent plane waves, the electric field has to tilt. And so, with respect to k prime, yes, it's orthogonal, but with respect to z, the real space coordinate, as you're propagating the beam and focusing it, E tilts in, you get a longitudinal field. Also quite interesting here is that this is x-polarized. Okay, so all right, so you get this longitudinal part, but you'll also see that these tilt in and out. So you also get y-polarized parts as well. So any real electromagnetic field is three-dimensionally polarized, no matter what your input paraxial beam would be. Okay. So all of this was in generally the first sort of paper to look at this was this paper by Melvin Lax in 1975. And he discovered that paraxial beams do not satisfy Maxwell's equation. Okay, the equation we normally describe our optical vortices with, we'd call it a zeroth order transverse field. And I'll get on to what the zeroth order means in a moment. It'll make sense in a moment. Okay, but here's our typical Gaussian beam, our most famous optical vortex. Here's the mode description. Okay, lots of stuff in there we're all familiar with. This is the polarization part. It's transverse. Okay, if you took the divergence of that, it's not zero. Okay, so it doesn't satisfy Maxwell's equations. All right, dx by dy of the ex and ey components does not equal 0. How do you fix it? Well, the only thing you've got left is the longitudinal part. So we need to work out what that longitudinal part is. Okay, and this is what Melvin Lax did, realized in 1975 about how to do all this sort of stuff. So you build in this fictitious not fictitious, it's there, EZ component, okay? And you can simply rearrange the equation to get this integral. You take an approximation on that Z integral, and you can write the longitudinal field as approximately equal to the transverse gradient, essentially, of the transverse field. Put that in, do the calculation, and this is what comes out. Okay, so this T0 is our paraxial field. This L1 is our longitudinal field, and you'll see it's obviously polarized along Z. Okay, and it's a lot more complicated than the transverse field. There's lots going on, which hints at lots of nice things if we go and study it. Okay. Now, there's two parts of taking the transverse gradient. There's the azimuthal part and the radial part. So I've just shown you here that the azimuthal part gives us the IL. The radial part gives us this form gamma, and this gamma is this long expression, complex expression, which describes all the electromagnetic field sort of when you tightly focus it. Okay? And so on that point, okay, the longitudinal field is proportional to this so-called paraxial parameter. So 1 over kW, k is the wave number, W is the beam waist. That's proportional to lambda, the wavelength over W. And so unless lambda and W are somewhat similar, the longitudinal part is very, very small. That's why paraxial optics works so well in most situations. But it will not work if you focus the beam down to sort of tight focusing regime, because this thing comes into play. So this is called first order longitudinal because it's first order in the parameter. That's zeroth order transverse because it's zeroth order in the parameter. That's where the order thing comes from. Okay. So this is what it looks like. So to get some grasp on what that does to the polarization structure, our electric field structure, let's put in alpha equals 1. What this is telling us is that if I have an X-polarized Lagrange-Gaussian beam and I focus it, this is what the field at the top looks like around the focal plane. This thing here, okay? So if it was a paraxial beam, well collimated, you'd just have that X. When you focus it, you'll have the longitudinal part as well. Okay? Now, of course, the polarization structure itself is hideously complicated, okay, because of all these different terms, but you can break them up and get some physical intuition from each one. So first one, trivially, the X-polarized component, the T0 component is plotted there. Okay? But you'll see that with the longitudinal component, there's an I there. Okay? And so what you have is a pi over 2 out of phase relationship between the X and the Z component. And you know that if you have an X and a Y component that are pi over 2 out of phase, you'll get an elliptical polarization ellipse. But here you've got an X plus an IZ, so you'll get an elliptical polarization ellipse. It'll just be in a plane transverse to the propagation direction. So rather than XY, it spins in XZ. Okay? And that's responsible for something we're going to talk about called the transverse spin of light, or the photonic wheel. Okay? The other thing, which is quite interesting for vortex beams, because we're interested in vortex beams here today, is that if you have a vortex beam, you'll see the second term, proportional to L, okay? That's imaginary. So the two i's cancel, and it's actually real, okay? So you have an in-phase relationship between X and Z, and what that does, it tilts the orientation of the polarization ellipse, essentially, but the polarization orientation, it tilts it in and out of the XZ plane. So you can control the state of linear polarization with the topological charge. And that leads to topological charge-dependent light-matter interactions in anisotropic materials. Because if you've got an anisotropic material and you can control the polarization direction with L, of course, different materials will respond differently to that. I won't talk any more about this stuff. Okay? That's just something I thought I'd bring up. Because, of course, if you have a Gaussian beam, you don't have this term. Oops. Right? Because L is 0. Okay, so this is a unique thing to vortices, this anisotropic material interaction. Okay? All right, so we satisfied Gauss's law by building the longitudinal component, but there are 4 Maxwell's equations, okay, and they all need to be satisfied. So if you put the equations back in like an iterative manner, okay, for Faraday's law, okay, you can work out the magnetic field, and the Maxwell-Ampere law, you can work out the electric field. The important point to note is when you do a full iteration of this, okay, you get these T2 fields, and these are often neglected. Okay, these are second-order transverse fields. They come from the transverse gradient of the longitudinal field. Okay, these are second-order transverse fields. All right, so this is the full picture of one cycle through Maxwell's equations to get a description of an analytical description of a focused beam. Okay, we'll of course, in general, look at the electric field today. All right, so yes, hideous, I know. So the first term is the paraxial field. The second term is the longitudinal field. The rest of it is this second-order transverse field, and it's really scary. It's scary because that's a completely general equation. You can put in any value of your polarization, and you'll get the right answer out, okay? It's scary, but it also hints at lots of interesting electromagnetic field structure that we could hopefully use in applications. Smallness parameter, it's a second order transverse field, so it's second order in the smallness parameter. So it's relatively, very weak in general. It's worth making a point here, though, is that you can't neglect it, because when you calculate an optical property, like a quadratic field, which is quadratic in the field, an L1 and an L1 would be a second order, it would be second order in the parameter, and a T2 of a T0 would be second order. So you can't necessarily neglect this at this stage, thinking of its second order, because when you do an actual calculation, it can be quite important, and of the same magnitude as a longitudinal field. Okay, now the reason why I'm interested in the second order field is that in general, there are components here which are pi over 2 out of phase with the T0 field. So as we saw the pi over 2 out of phase T0 fields gave our normal spin, the pi over 2 out of phase T0 and L1 gave us our transverse spin. We're also going to find that the pi over 2 out of phase components with T0 and T2 will give us some very, very interesting angular momentum properties as we go through. So to put make this a bit more sensible, if I say I've got an x-polarized beam, so I put alpha equals 1 in the expression, this is what I get, And what you see is you've got an x component here in T0 and a T2y component. So you've got orthogonal components, which will be pi over 2 out of phase due to these i's. We'll get into that in a bit more detail later, Okay, so the first property I want to talk about is the intensity of focus beams. So I'm just going to use the longitudinal field to display this point. Got a circularly polarized field. Straight away, you can see in the longitudinal part, there's a spin-orbit interaction. Right? You've got an L times a sigma. What that means is if your spin and OAM are aligned, so 1 and 1, that will give you a different result to if they're anti-aligned, so 1 and minus 1, for example. And we've also got this well-known spin-dependent vortex phase here. Right? So if you had a L equals 0 beam, a Gaussian beam, you still have this term, and that highlights that you get OAM from spin, so you get spin-orbit conversion. I won't talk much about the angular momentum of that, but we'll talk about the intensity. So this is what the intensity looks like of a focused vortex beam. So this first term here, 1, which I've highlighted in blue, that's the paraxial term. Right? It's very simple, of course. It's just proportional to the intensity. The rest of it is all due to the longitudinal field. And what you find, these multitude of terms, we can look at them individually. So this first term here, L squared minus L sigma, if L is 1 and sigma is 1, then that will be 0, because 1 minus 1. If sigma is 0, so linearly polarized light, it will be 1, because 1 minus 0. And if L and sigma have opposite signs, it will be 2. So you've got 2, 1, and 0, depending on the angular momentum combinations. So what you see is, if you look on those plots, if you can see, I'm not very good, but this yellow line here, this is plotting this term. All right, we've got a vortex beam, but look at the intensity. This is the 0 point of the intensity distribution, and you're going out in R. It's non-zero, and this is for a linearly polarized beam of light. So a tightly focused linearly polarized vortex is not actually a vortex. There's intensity at the center. If I have anti-parallel OAM and spin, so L equals 1, sigma equals minus 1, so a left-handed vortex with right-handed circularly polarized light, it's even larger on axis. If I have anti-parallel, so if I have parallel combinations, it is actually a vortex. So this is really good for STED microscopy if you have these parallel combinations to get that dark center. So the point is, in the paraxial regime, we say about these have no intensity in the center. When you focus them, that all changes. L equals 1 beams are not actually vortices in general. The same applies to L equals 2. All right, the second term I want to highlight, because we're so used to talking about spin-orbit interactions doing this on-axis intensity. But as beautifully shown by Konstantin in his paper, there's another spin-orbit interaction term, which is given this red line. And what's that actually doing is it's causing the overall intensity to shift around. And so the overall intensity maximum of these rings is highly dependent on the angular momentum of your beam going in. So you can make them bigger, smaller, depending on the combinations of OAM. So I just want to highlight that because, we often talk about spin-orbit interaction in terms of these on-axis stuff, but it also does other stuff in the beam. And then we have just our simple Gaussian R-squared part, which comes from the calculation. So that's not all made up. It was observed a long time ago, actually. And so in this experiment in 2007, so this first one here is when I've got the parallel OAM and spin. So it will be a left circularly polarized beam with a left-handed vortex, and it will give us our intensity null. I then have a linearly polarized vortex beam, and you'll see the intensity down the middle is not actually 0. It's actually quite large. And then at the extreme end, if you have anti-parallel, it's almost like a Gaussian beam. That's definitely not a vortex beam anymore. So in contrast to the paraxial description of these beams, focused beams have significantly different intensity distributions. And of course, because it's the intensity, this underlies a lot of the properties that we come to see anyway. Okay. So the next one I'll talk about is spin angular momentum. Okay, and this is obviously this E cross E, it has to be imaginary. What that means is you need two orthogonal components which are pi over 2 out of phase. Again, we know that for a paraxial beam, we satisfy that when X and Y are pi over 2 out of phase, elliptically polarized light, circularly polarized light, and as they spin in the transverse plane, they give a longitudinal spin angular momentum in the Z direction. Okay, and we can liken it to this aeroplane propeller. But we've seen we've got this higher order field structure for our focus beams, and so we can expect a higher order longitudinal spin from the T0 and the T2 field, because they're both in the transverse plane. And as we spoke about, they do have pi over 2 out of phase components, and they will also spin and give you a longitudinal spin. And then we get our transverse spin. So rather than spinning in the plane orthogonal to propagation, it spins in the plane which is parallel, so we can spin in the XY plane, sorry, the YZ plane or the XZ plane, and that will give you a spin which is pointing outwards, orthogonal to the direction of propagation. Okay? So this one gives us a helicoidal trajectory in space. This one gives us a cycloidal trajectory in space. So let's go through. If we use our T0 fields, this is a very simple calculation. What is spat out? Well, it's the well-known textbook spin of a paraxial beam. It points in the Z direction. It's proportional to the ellipticity. It's 0 for linearly polarized light. Very standard work stuff. Okay. Let us do the calculation now with the T0 and the L1 field. So that's the transverse field, the paraxial field, and the longitudinal field. And straight away you see you've got X hat and Y hat components, so they're pointing in the transverse direction. And again, there's a lot of structure to that equation. There's a lot you can do and play around with. But let's make life simple and say, let's have an X-polarized Gaussian input beam. So I take an X-polarized Gaussian beam. It has no spin in the far field. I focus it. Okay, in the focal plane, it will generate a spin angular momentum transverse to the direction of propagation, pointing in Y hat. Okay, and it has a spatial distribution like this one here. Okay. So it's these two lobes of plus and minus spin. All right? It's helicity independent. It's remarkably different to our paraxial spin. Right? This thing here, you need ellipticity. It's helicity dependent, points in Z. This thing here has no dependence on helicity, okay, and it points in the Y direction. All right? And I said there's a lot of structure to the equation. And so if you sent in a Y-polarized Gaussian beam, the spin is now directed in the X direction, not the Y direction, and the lobes twist round. Okay, so there's lots of playing around you can do with this transverse spin, and it was measured back in 2015 by Peter Banter's group here. So this is the measurement of that, right? Okay. Now we're interested in vortex beams. Now for some reason, I don't know the answer. I don't think anyone's actually measured the transverse spin of a vortex beam, or they haven't published it at least. Okay. The reason why is probably because it's so similar to the Gaussian beam and more complicated, I imagine, experimentally. Because all you get is this additional set of lobes due to this additional L over R term, which is obviously 0 for a Gaussian beam because L is 0. Okay? However, if you have a circularly polarized Laguerre Gaussian beam, it does become a bit more interesting because you get spin-orbit interaction. So you get this L sigma term again. So we can play off the value and the sign of L and sigma again to get completely different spatial distributions. So if the spin and the OAM are aligned, we get two lobes, okay? And notice now that the spin is now directed azimuthally, okay? Rather than just X or Y, it's directed azimuthally. But if we have opposite signed, we get this four-lobe pattern, okay? So we can control the transverse spin in the focal plane by playing around with the helicity in the far field or the topological charge in the far field. And again, just keep referring back to these textbook things I'm putting in the top corner. Okay, because these are what we get for our normal paraxial beams for spin, and look how different it is once you focus a beam. It's very interesting. Okay, so now it gets really, really interesting, because we've looked at linearly polarized light, we've looked at circularly polarized light being focused. A quick way to determine the result of an unpolarized beam in a quadratic field quantity is just to average over two orthogonal polarizations. So this is the spin for an X-polarized beam. Stop doing that. This is the spin for an X-polarized beam. This is the spin for a Y-polarized beam. They're orthogonal. So I can average over the two to get the unpolarized results. It's a very straightforward way of doing it. Clearly, if I average over those, it's just adding them up and dividing by 2. It's not very difficult. Okay? The spin now becomes azimuthally directed, fine, but the spin is non-zero. So you can take an unpolarized beam of light, focus it, and in the focal plane, you'll have a non-zero spin, transverse spin in particular. Okay? And Constantine, again, is responsible for this work where they measure it. Okay? Peter Banzer would have done the measurements. And so you see in the top here, that's the electric spin being measured, which is this thing here is being measured here. Okay? And of course, right at the start, we spoke about optical properties. Well, each one has an electric and a magnetic contribution. Normally, we don't really measure the magnetic part, A, because I imagine it's quite difficult in most places, but here's the magnetic distribution as well. Interestingly, most of the time for non-paraxial fields, the electric and the magnetic field distributions are different. Here, they're actually identical. Okay? So more generally, this is for a Gaussian beam, but more generally for a vortex beam, it would look like this. So the intensity is now an LG, and we've got that gamma factor again. Okay? So it's not much changes. Okay? Just try and remember the fact that these unpolarized beams have this azimuthally directed spin. It'll be important later on. Okay, this is now the real sort of newer, really, a lot of that was well-known stuff. This is probably more new, okay, to some of you. We can actually get longitudinal spin from spinless beams. So now I want to take a beam which has no spin in the far field, focus it, and get a longitudinally directed spin. Okay, that's what I want to do next. And how do I get that? I get it from these T2 fields. So the T0 cross the T2, that's why the T2 fields are important and shouldn't be neglected, because they do have novel effects. Hideous expression again, I apologize. Let's put in an X-polarized beam, make it simple. This is what it looks like. So an X-polarized beam, being focused in the focal plane, has a spin directed along Z, which looks like this. Okay? Straight away you see it's non-zero, and it's directly proportional to the topological charge, and its sign. Okay? So if we look at our normal paraxial spin, the pseudoscalar involved in flipping the sign is the helicity. For our special longitudinal spin from spinless beams, it's the topological charge. Okay? And obviously it requires non-zero OAM. So in the far field, you need to have a non-zero OAM to get this spin in the near field. Okay? So it's not achievable for Gaussian beams. But I put a little asterisk here because I'll show you something in a minute which will sort of qualify that a bit better. What does it look like? Well, now we get these full lobe patterns, okay, for L equals 1. So here it is plotted for L equals 1. I send in an X-polarized beam. For L equals 1, this is what the distribution of spin looks like. Okay, so we've got spin in the Z direction with this distribution. If I change the sign of L, I flip the sign of the lobe. So I can control the spin with the sign of L. Also, this depends on the orientation of the linearly polarized input beam. So this is X-polarized. If Y-polarized, keep everything the same, it will also rotate it. This has the immediate effect that it's zero, for unpolarized beams. If I add that up and divide by 2, it's obviously going to be 0. So we don't get a nice unpolarized result here, but nonetheless, you still get spin from spinless beams. And I can also increase L and have 8 lobes. So it gets quite complicated quite quickly. Okay. So this is the last bit of angular momentum I want to talk about. Now, when we took that longitudinal field, we had to do the radial gradient, if you remember. We got this gamma term. Now, in the mode expansion, you've got this thing called the wavefront curvature. And that depends on R. So in d by dr, that will give me a term. And that term is that imaginary part of gamma. Now, most of the time, this imaginary part disappears in calculations. And moreover, because it depends on the wavefront curvature, it's always 0 at the focal plane, because the wavefront curvature is infinite there, right? However, it's not 0 away from the focal plane. So if I take a Gaussian beam now, okay, so it's a simple X-polarized Gaussian beam here, this expression. Okay, I've got my T0 field right at the front, L1 field, T2 fields. I look at X, I look at Y, I've got a gamma, gamma's got an I in it, it's going to have pi over 2 out of phase relationships. It's going to spin, okay? And the spinning won't occur at the focal plane where we always look, it will occur away from the focal plane, because that's where you have curved wavefronts. And this spin depends on R, which is the wavefront curvature. So in theory, we hope to say, if I take a beam with no angular momentum, so the spin from spinless beams, we had an OAM beam, remember? Now I'm saying I want to have no angular momentum, so a Gaussian beam, linearly polarized. In the far field, it will do nothing to your probe particle. When you focus it, it won't spin it in the focal plane, we predict, but away from the focal plane, it should spin it because it will have a longitudinal spin. It will produce a torque on it, in theory. Okay? So you need to look away from the focal plane. So let's revisit that longitudinal spin, okay, from beams with no OAM. So this term here, we saw that earlier. It depends on L. If L is 0, it's 0. This term is now taken into account the wavefront curvature. We're looking away from the focal plane. And you'll see, okay, what it does to the OAM version. All right? It twists it. So it will twist the distributions away from the focal plane. But if I set L equals 0 in this expression, this all goes away, this goes away, but this stays. And so for a Gaussian beam, I get non-zero spin, okay, from a beam which had no angular momentum whatsoever if I focus it. All right? So it can't be at the focal plane, but away from the focal plane, I get these distributions of spin angular momentum, okay, due to the wavefront curvature. And you also produce longitudinal OAM, which I haven't shown here. So basically what it's saying is you focus a linearly polarized Gaussian beam, there's no angular momentum. It will have OAM and spin in the direction of propagation around the focal plane, but not at the focal plane, around the focal plane, okay? And let's revisit transverse spin, right? So our circularly polarized input had this azimuthal term, but we also now have a radial term, which is helicity dependent. So transverse spin is often helicity independent, okay? But away from the focal plane, it can be helicity dependent, okay? So if I plot the radial part, so here, this is for a left-handed circularly polarized beam. This is for a right-handed circularly polarized beam. Of course, the sign changes as you traverse the focal plane because the wavefront curvature changes sign. But if I take a given slice of Z, you see it clearly changes sign, okay, depending on the handedness of the input beam. More interesting is to break this expression up into X and Y components because you see this rotation. So in the focal plane, okay, this is the X component of the transverse spin. It's absolutely identical. But away from the focal plane, it twists in opposite directions if I change the state of circular polarization. So it becomes helicity dependent, this twisting. Okay? So we now have a helicity dependent spin, okay? Transverse spin, sorry, away from the focal plane. And actually, so we published this result like at the end of last year or start of this year. And then I realized, I went back, there's this experiment by Peter Banzer's group where they actually see this rotation. Okay, this is what I'm talking about, now rotating through. So this is the X component for right circular. This is the X component for left circular. And so this is showing that twisting effect. This is along Z. It's showing that twisting effect. However, someone here might be able to help me out here. In this paper, this is all due to, or theorized due to GUI phase. But in our work, it says it's due to wavefront curvature. And of course, they're somewhat linked, but they are distinct. So if someone clever in here can marry the two up for me, that would be great. So I don't know, I haven't thought about it enough, but that's quite an interesting thing to try and work out. All right, so this is what we all came for. Now I want to talk about optical chirality of vortex beams. So we're so used to doing chiral light matter interactions with circularly polarized beams, in particular circularly polarized Gaussian beams. And in that case, you know, they become chiral, right? This is left-handed, this is right-handed. Shine this on a molecule, a chiral molecule, it'll absorb the left-handed one at a different rate to the right-handed one, circular dichroism. A linearly polarized Gaussian beam is not chiral. If we look at vortex beams, independent of polarization, they are chiral. They are geometrically chiral structures. Their wavefront twists to the left or to the right, independent of polarization. So there's a strong motivation to look at these beams to see if we can do analogous chiral light matter interactions as what we do with circular polarization. And I quite like this diagram because if you look at this, this is our like set of beams we've got, right? So we've got, you know, our polarization overlaid on our wavefront. This is chiral. All of these are chiral, and this is chiral. This is the only non-chiral thing. So the chirality of a structured beam is actually quite ubiquitous, okay? You're often going to have a chiral beam than not, all right? Now, it's our task to work out how to engage this additional vortex wavefront chirality. First and foremost, I like to do the slide, why bother, okay? Well, firstly, in theory, you should get enhanced signal. If you have a chiral light matter interaction, it will be proportional to the helicity, so the circular polarization, which we're seeing can be plus or minus 1, depending on the handedness. With a vortex beam, they can go up to infinity in theory. You'll never get to infinity, but you can go a lot higher than 1, okay? So you can add more twists, more chirality to your beam, meaning you can get an enhanced signal. Number 2 is that these beams have really structured fields, as we've seen, okay? Really complicated structured fields, and that will drive things like quadrupoles and higher order transitions a lot stronger. So you can probe dark states and forbidden transitions and get a lot more information from those, which are usually hard to detect with a simple Gaussian beam. And number 3, it just offers up a new technique. If I have circularly polarized light and chiral matter, I can get circular dichroism, circular differential scattering. If I have a magnetic field, I can get magnetic circular dichroism. Then I start to run out. If I could engage the vortex handedness, I could get vortex dichroism, vortex differential scattering, magnetic vortex dichroism. And because the polarization is independent of the wavefront chirality, I could have circular vortex dichroism or circular vortex differential scattering. So the toolkit is massively expanded if you can engage this chirality, okay? And just a little side note, you'll see helical dichroism written a lot, you'll see vortex dichroism written a bit less. They both mean the same thing. It's just a differential interaction to a vortex beam due to its handedness, okay? I prefer vortex because circularly polarized light is helical, so I don't think it distinguishes it very well, but I'm not going to get into that anymore. So I do it every time I have to give a conference. So the early days. So as I said, this is rather an obvious question to ask, and it was asked a long time ago, 2004. Can we see chiral light matter interactions with optical vortex beams? David Andrews, Mohamed Babacar, and Luciana Romero tried this in theory, and it was followed up by an experiment which said, no, you can't do it, it doesn't work. Okay, and the reason is because they looked at a paraxial beam, a transverse wave, and it's really, really simple to see that you won't get a chiral effect due to L. So here's our electric field, here's our magnetic field. The only place where the sign of L comes in is in the azimuthal phase. Right? This is the only place where L matters if it's plus or minus, left or right. This is the optical chirality. We saw that at the start. You take the inner product between the electric and magnetic field. Okay? You take the imaginary part of it. So you need a pi over 2 at a phase relationship, again, of the electric magnetic field. Now it's E star dot B. So I need the complex conjugate of this. E minus IL times EIL is just 1. So the L disappears. So the L will not engage in the optical chirality if there's a paraxial beam of light. All that comes out is sine 2 eta, whereas we look at our polarization, our Poincare sphere, sorry, this just means it's our third Stokes parameter, right? Eta 0, linearly polarized light, you have no chirality, knew that. As you increase the ellipticity, okay, you'll increase the chirality, taking on a maximum value when you get to the poles, left and right circular. Okay, so it's, the chirality of a paraxial vortex beam is essentially no different to any other chirality of any other beam. Just totally dependent on the circular polarization. Okay? But you need to start thinking about the problem a bit better, because chirality is scale dependent. Okay? My feet are chiral, all right? My left foot will only fit in my right shoe. My left foot will only fit in my left shoe, and it will not fit in my right shoe, because there's a chiral discrimination there. But my daughter's feet are this big, and they will fit in any of my shoes. They're still chiral, but they don't interact in a chiral fashion because the size scale is just not right. Chirality is scale dependent. Now, polarization is a local property. Everywhere is circularly polarized in your beam, okay, wavelength scale. Phase, as a azimuthal phase, is a global property of your beam. So if you've got a beam which is millimeters in its waist, its twist is huge compared to small chiral particles and molecules. So that is why a paraxial beam, for small chiral objects, you don't see anything. Okay? That hints, though, at the way to fix it, and that is tight focusing. So if I take my beam, which is big, doesn't do anything, and focus it down to a tiny little point, that chirality, that global phase chirality, starts to get on the size scale of your chiral molecules and particles that you want to interact with. And so the mathematics plays this idea out beautifully. So let's look at a non-paraxial, tightly focused beam. You know what this is now. It's the T0 field and the longitudinal field, electric and magnetic. And I've chosen to do an X-polarized beam because I want to get rid of the circular polarization, so I want to isolate the vortex chirality and see if it does anything. Immediately, you can see that in the mode structures or the field structures, there's linear dependence on L outside of this azimuthal thing. So it hints at the fact you should be able to do something. And if you do E dot B again, what happens? X dot Y is obviously 0, but Z dot Z is non-zero. The longitudinal fields contribute this term to the optical chirality. Compare this optical chirality to our textbook one. It depends on L as a pseudoscalar. This depends on sigma. Depends on L, so it will change sign with L. So here it is plotted, these two ring structures for L equals 1. If I place the chiral structure there, shone L equals 1 light on it, and then shone L equals minus 1 light on it, it would absorb and scatter that light at a different rate due to the topological charge. Nothing to do with circular polarization. Okay? And again, this has been seen in experiments. Peter Banzer's group put this gold nanohelix at the center of one of these beams, flip the sign of L. The transmission is markedly different due to a vortex differential absorption of the light. Okay? You get this vortex or helical dichroism that depends on the wavefront handedness. So I really like this result because it marries up beautifully with the physical picture of focusing the beam and getting that chirality down to the wavelength scale. Okay, and the maths plays it out. You study a focused beam mathematically, it will give you what you want, that sign on L, which they couldn't get back in 2004. Okay. Now, another thing I love about optical chirality of vortex beams is that it's really tailorable compared to a paraxial typical beam. So all these additional rings is because I'm now using Bessel beams, just to be clear, because they're a bit neater sometimes. So this results in just using Bessel beams. It's still optical vortices. And what I'm doing here is I'm going to basically say, here I've got a linearly polarized, these left-hand ones are linearly polarized vortices, so they're on the equator of the Poincare sphere. Obviously I'm changing sign, so you see the result we saw before, a left-handed vortex linearly polarized to a right-handed vortex linearly polarized, change the sign. But what I'm going to do now as I run across these is run up and down the Poincare sphere and increase or decrease the ellipticity, okay? Because as I said to you, the polarization is independent of that wavefront. So as I increase the ellipticity, you see, so this is going down the Poincare sphere, so I start here and come down on this one. As I come down, I'm changing the chirality structure in the focal plane significantly. And in fact, for this value of ellipticity, I've almost got a Gaussian spot. And of course, I can then go up the Poincare sphere, which is switching the sign of circular polarization, and get a completely different set of chirality distributions. Okay? And you'll also see here, this is an L equals 1, sigma equals minus 1, it's a left and a right, you'll get an on-axis chirality. Here it's L equals 1, sigma equals 1, so they're parallel, you get no on-axis chiralities. This mirrors the intensity distribution, as it should. Okay? And I can change the sign of L and do it all again. So I can change the sign of L, I can change the degree of ellipticity, and I can change the handedness of ellipticity. Can't do any of that with paraxial chirality. Well, I can change the handedness of ellipticity, sorry. I can also increase the value of L. Can't do that with circular polarization. I can increase the value of L and do it all again. So I've got 4 parameters there I can play with to change and manipulate my optical chirality. Now things get really interesting now because I can also play around with the degree of polarization. So all of this so far has been on the Poincare sphere. If I go in the Poincare sphere, I'll have partially polarized light. And so I can increase and decrease the partial polarization of my beam. So P equals 0, P equals 0.05, 0.1, 0.5, 0.75, and change the polarization distribution. I'm not actually that bothered about that. What I'm really interested in is that P equals 0. That's an unpolarized beam. So an unpolarized beam possesses optical chirality if you focus it. That's pretty extraordinary result. Okay? What it means, if I take an unpolarized vortex beam and focus it, change the sign of L, I can get chiral differential light matter interactions just due to the sign of L with an unpolarized beam. Okay, so I think that's pretty cool. Okay? And I can vary the ellipticity and the degree of polarization at the same time. It gets a bit boring now. The point is, you can change the sign of L, you can increase the value of L, you can change the degree of ellipticity, you can change the sign of the ellipticity, you can change the degree of partial polarization. 5 parameters, you can completely tune your optical chirality. The most important takeaway of this is unpolarized vortex beams have chirality. I think that's the most interesting part. I don't know what I'm doing for time. Okay. Yeah, I think I'm good. Okay, so the unpolarized result is quite interesting because you can put it another way. Because the optical helicity or chirality can be alternatively defined as the spin projected onto the momentum density. Okay? Now, the momentum density, as we saw, takes this form. It's clearly independent of polarization. So an unpolarized vortex beam has this same canonical momentum density as a polarized one. And I said to you to remember this. The spin of an unpolarized beam is purely transverse, and it looks like this. So if I project my spin onto my canonical momentum density, I take the inner product. The z bit goes away, obviously, but the phi bits don't. They're 1. And so you can get the helicity using a completely different formulation than the E dot B, and it completely matches. The point is, what we've shown is that this extraordinary chirality of vortex beams is associated not with a longitudinal spin, which is what normally is the case with chirality, but a transverse spin. So the transverse spin is actually associated with this extraordinary optical chirality of vortex beams. Okay? And the important point is that transverse spin is very generic to structured waves. Okay? Gaussian beams, Laguerre Gaussian beams, acoustic beams, evanescent waves, they all have this transverse spin. It's ubiquitous. But only vortex beams have the azimuthal component to their canonical momentum density. Oops. That's why vortex optical beams have this amazing chirality property and these other fields don't. Okay, so there's lots of interesting work in this field of vortex chirality now. I'm just going to show 4 examples, mainly because they show a very clear signal enhancement. So I said to you those 3 reasons why bother. The first one was because you get a larger signal. So these papers, as far as I'm concerned, as I've read them, I think I'm interpreting them correctly, these enhancements I'm going to show you are all relative to an analogous experiment with circularly polarized light. So it's a genuine advantage over circularly polarized light. So this X-ray vortex dichroism, okay, which I think a few of you in this room are authors on, it had a 5-fold signal enhancement. Okay, so you have a linearly polarized vortex beam, shine it on these organometallic complexes, and you'll get differential absorption, scattering, okay, and it's 5 times larger than the analogous result with circularly polarized light. This nonlinear vortex dichroism mechanism in molecules as small as limonene and phenshone was 6 times larger. And then we've got a 120-fold enhancement in vortex differential scattering in these plasmonic nanostructures, okay, and a 25-fold enhancement in differential scattering for chiral molecules absorbed onto those nanostructures. So there's some clear enhancement advantages to be gained from using the vortex beam. Okay. So the final thing I want to talk about really is just this distinction between spin and chirality and polarization. So in the paraxial regime, they are essentially one and the same, right? Because the spin here is just the helicity, okay, times the direction of propagation. How do you get spin and helicity? You need sigma, it means you need circular polarization. So, you know, we use the first Stokes parameter in a paraxial regime you can map all these things out and measure them essentially. That is definitely not the case for non-paraxial optics. There's no relation like that, okay? Because what we've seen is that the linearly polarized light of a vortex beam looks like this. Oops. These four-lobe structures here, okay? Okay, and there's no helicity associated with this. There is no helicity associated with the spin of these beams, okay? Whereas the helicity or the chirality here looks like, so they're clearly not one and the same, right? If you measured this, you're not going to measure that like you do in paraxial optics, okay? They come from different fields. So this is T0, T2 for the spin, and it's longitudinal purely for the chirality. And this is associated with a transverse spin, not a longitudinal spin. So there's none of this one-to-one ratio between, one-to-one proportionality between spin, chirality, and helicity. The only thing that's safe to say is that to get spin, you need a circular polarization in a given orthogonal plane, basically. That's pretty safe, but everything else is not so. Okay? And so obviously what's more drastic is that an unpolarized vortex beam will have chirality but no spin or no longitudinal spin, and that this chirality is associated with a transverse spin. That is just not something you'd find or think if you thought about paraxial beams of light being possible. So in general, the 3D field, the non-paraxial field, the first Stokes parameter does not measure the chirality. Okay? And a paper which came out yesterday, I've sort of spelled this out in that, if you want to have a look at that. I think it came out Monday, I think. So yes, don't use your first Stokes parameter in the near field because it won't work for chirality. Okay, so key takeaways are properties of light in complex fields cannot be inferred from their behavior in simple optical fields. Think about that slide I showed you with the paraxial beams. Very simple. Think about these crazy properties we've spoken about today. You cannot infer what's going to happen, okay, in a focused beam or a near field. Okay, as soon as you spatially confine your fields, okay, things start getting a bit weird. Okay, you cannot infer anything from the far field. Okay, these longitudinal and higher transverse fields are actually ubiquitous. Okay, they're all there. Maxwell's equations tell us that. But remember, only under tight focusing conditions do they become important. So there's nothing wrong with paraxial optics. It works absolutely beautifully. Unless you tightly focus your beam, you're going to start missing things. Okay, so don't start going around using that huge equation I showed you if you don't need to. These Horror fields, they're not just small corrections. They're responsible for several extraordinary properties that you can measure and have been measured in focused beams. Okay, so do not neglect them. We've seen that spinless beams under focusing can acquire both transverse and longitudinal spin. Okay, and we've also seen that focused unpolarized beams can have transverse spin and optical chirality. Okay, we've seen that longitudinal spin is not in general associated with helicity, and transverse spin can be associated with helicity. Yes, this is probably the key one for the vortex, the chirality people. After 20 years of saying they don't do anything, optical vortex beams definitely do engage in chiral light matter interactions. It's highly tailorable, but the most important thing is that it's scale dependent. So whatever size your structure is, you want to probe if it's chiral, make sure the beam is similar. If not, you won't see anything. Okay, that is the ultimate one thing to take away from this talk if you're an experimentalist. Make sure you focus your beam to be the same size of whatever it is you're probing, and you should see a chiral effect. Okay, so clearly today I've concentrated on free space beam properties. As I said at the start, I just want to give an overview of what this light can do, okay? But obviously, don't forget these beams interact with things, okay? So all these things I've spoken about represent novel methods of optical manipulation, optical activity, so chirality stuff, and spectroscopy at the nanoscale, okay? That's what I think a lot of you want to do with these beams, and so you can take these optical properties as a starting point, okay, and start to see what you can do when you start shining them on actual materials, okay? So thanks to all these different collaborators that I've been with for some of this work, okay? And of course, thank you all for listening.